Hi everyone, in this paper we introduce the geometric understanding of deep learning, especially for generative models. Now deep learning is very successful, but its understanding remains mystery. This work opens the black box of deep learning, especially GAN models, using differential geometry and optimal transport theory. We also propose a novel transparent generative model called the AEOT, and this model can overcome mode collapse problem effectively. The intrinsic law behind the big data is the manifold assumption that this natural data set can be treated as a low-dimensional distribution embedded in a high-dimensional space. For example, the data set of the 10 digits can be embedded to the two-dimensional Euclidean space. The central tasks of deep learning include manifold learning and probability transformation. The manifold learning aims to find the encoding and decoding maps between the manifold and the latent space can be realized by the autoencoder model. The probability transformation transforms white noise distribution to data distribution and can be solved by optimal transport theory. Optimal transport transports one distribution to another. It lies at the intersection of statistics, geometry, and partial differential equations. The purpose of generative model is generating new examples for a given data set. For example, given some points in the 3D Buddha, we can generate more samples located in the Buddha manifold. In our AEOT model, we use autoencoder to learn the manifold. In the Buddha example, we flatten the Buddha into two-dimensional latent space by autoencoder. Then we learn our optimal transport map from uniform distribution to the data distribution in the latent space. Composing the optimal transport map and the decoder together, we can reconstruct the Buddha manifold perfectly as shown in the right figure. In this experiment, there are total 25 modes represented by the orange dots. Green dots represent generative samples. Compared with the GANs, AEOT models can overcome all the modes, can cover all of the modes clearly. We also compare with the state-of-art methods in 4 datasets: MNIST, Fashion, CBAR 10, and Celeba. The FID is used to evaluate the quality of the generated images, and our model beats the comparisons in 3 of the 4 datasets. Here we also give some generated examples by different methods. For first 3 datasets, the quality of the generated images of our model is the best. We also give the interpolation results of the high-quality images.